Welcome to today's video. Welcome to Tutor-E's Chemistry Hub, where we'll do our very best to make chemistry as simple as it can be. We'll continue our discussion on the formula of compounds and the oxidation number. And as I've already seen from the previous video, getting the formula of compounds, the most important thing is about knowing their oxidation numbers. And today, we are going to be checking out some radicals. How can you calculate and know their oxidation number? Because depending on the curriculum which you operate, these radicals you may be given their oxidation numbers and it becomes easy. But in some curriculums, as I've seen, you are not given these oxidation numbers. So even if you are not given, how can you calculate it and you just know it yourself? Because in the end, once you're able to get the oxidation number, it's all about swapping, as you're going to be seeing in our next video. Now we know the oxidation numbers, how do we get the formula of the compounds? But the first thing is, once you have the elements and radicals involved, and you know the oxidation number, then you are halfway there. In fact, I will say you are more than halfway. You'll be about 90% there, because the other thing that's remaining is simply just swapping. All right, so as I've already spoken about it in the previous video, watch it again. Valency is the number of electrons in the outermost shell of an atom. Although it can be used interchangeably with oxidation number, however, they are different. Oxidation number is the number of electrons an atom will likely gain or lose when it is involved in a bond. Not just any bond, actually an ionic bond. Because it's only an ionic bond or electrovalent bond that is where atoms lose or gain electrons. In covalent bond, what happens is they share electrons. So we are talking about oxidation number, we are focused on ionic bond. In another video, we'll be talking specifically on electrovalent or ionic bonds. Alright, so now, like I already said, we are focusing today on how to calculate the oxidation number of radicals. And the simple way to do it is you simply get the oxidation number of different atoms that are involved in the radicals and add them together. And that is all you simply need. Now, one idea we have to bring out here is full disclosure is practically that oxidation number can vary. As you will see in the link below, I put some oxidation numbers and the various elements and radicals. But you should know that these oxidation numbers, depending on, especially for the elements, depending on the compounds they are involved with, the oxidation number can change. An example, in the previous video, we calculated that the oxidation number of chlorine is 1. But there are some certain situations where the oxidation number of chlorine is 7 and not 1. That means in that particular bonding, it tends to lose 7 electrons instead of gaining 1 electron. So you can see it depends on the case. However, the ones that are in the file, which will be put below, we talk about the most common oxidation numbers, which are most likely going to find in your O level. And the one exception with chlorine, I will point that out, that is practically in ClO4. So I don't forget. That's tetraoxochlorate ion. We'll find that out later. You can see the charge is simply -1. So the charge, the oxidation number of the whole radical is just 1. So I don't forget I'm putting it there. However, let us focus on calculating oxidation numbers. Remember, once again, all you simply have to do, the various oxidation numbers, you add them together. That gives you the oxidation number of the whole element. So an example, let us start with hydroxide. That is OH. Now for oxygen, the oxidation number is 2. But in most cases, oxygen tends to be -2. Why is it -2? Now, in an atom, you have the possibility of gaining or losing electrons. When you gain electrons or lose electrons, you become an ion. And as far as it's an ion, it can either be a cation or an anion. Anion they are negatively charged, they gain electrons. Cation, they are positively charged, they lose electrons. So oxygen in this case is going to be gaining electrons because, again, remember oxygen, the configuration is 286. It needs the octet configuration, so it is easier to just gain 2 than to lose 2. Since to be gaining, it becomes negatively charged by 2. Hydrogen, on the other hand, its configuration is just 1. All it does is to donate the 1. So in this case, hydrogen is plus 1. So therefore, for hydroxide, what do you have? You are having oxygen as minus 2 and then hydrogen as plus 1. When you add it together, minus 2 plus 1, you are going to be having minus 1. And that's the reason why you normally see it as OH minus. Simply put, the oxidation number of hydroxide, let's call it oxidation number, or let's shorten it, is simply 1. That is for hydroxide. Let's move on to something else. We have the sulfate ion or tetraoxosulfate ion. What is going to be its oxidation number? Now, once again, in this case, you are having sulfur and oxygen. And the beauty of this is that, oh, sorry, please go back. Oxygen is 26, not 286. It has just 8 electrons. Sorry about that. Sulfur is 286, its configuration, and oxygen is 26. So the point here is that the both of them have 6 electrons, but one of them has to gain in this case because, again, it's an ionic compound of sorts. But normally, two nonmetals form covalent bonds. But in this case, because it's ionic, that means one will be gaining and one will be losing. So the point becomes, which one is much likely to lose, which one is much likely to gain. Oxygen is much more likely to gain because it is much more electronegative. Again, we'll be discussing the concept of electronegativity and other periodic properties in some later videos. So because oxygen is much more electronegative, it will tend to gain electrons compared to sulfur. In fact, when we discuss the periodic table, we are going to find out that even when they form covalent bonds, what happens is that you have what you call a polar covalent bond. The electrons are closer to one side, to oxygen, than to sulfur. But that, again, is not the focus of this class. So the point is that both of them have 6 electrons in their thermal shell, but one of them has to donate. Who does the donation? It is sulfur, because oxygen is much more electronegative, so it tends to drag the electrons. So in this case, that means that oxygen takes the role of minus 2, as you have already seen, and sulfur in this case, because it will be losing all its 6 electrons to the oxygen, takes the role of plus 6. So you can see their oxidation numbers. So you can see why oxidation number is different from valency. They both have a valency of 6, but in this case, because sulfur wants to lose its whole 6, it's taken as plus 6, and oxygen is going to be gaining 2, it is taken as plus 2. So now let us solve it. We therefore have, let's bring it over here, SO4. So we are going to be having plus 6, and then added to the one of oxygen, but oxygen is minus 2. Before we put on the minus 2, we have that there are 4. From the 4 here, we have 4 atoms of oxygen. So that's 4 times minus 2. So here we are going to be having plus 6. Plus 4 times minus 6 gives us minus 8. And that gives us minus 2. And this is the reason why you normally see SO4 2 minus. And that in itself means the oxidation number is 2. This is practically how you calculate it. And you can see how you get the concepts of oxidation numbers. Now, let us look at, say, triazocarbonate. What will be the oxidation number? Now, once again, Normally, between two nonmetals, you should be having a covalent bond. But again, the idea here is it is going to be electrovalent. So the concept is one loses and one gains. And if I should ask you, between carbon and oxygen, which is going to gain electrons and which is going to lose electrons? Well, again, it goes back to the concept of electronegativity. Oxygen is much more electronegative, so oxygen gains. Oxygen remains 2,6 and carbon is 2,4. So what does that mean? Oxygen has the tendency to gain 2 electrons. Because it's gaining 2 electrons, its oxidation number is -2. And as for carbon, it has to lose its electrons. That means it takes the role of +4. So therefore, let's come and calculate it. We have CO3. So carbon is +4. Added to, you have 3 atoms of oxygen, that's 3. And the oxidation number there is -2. So you have +4 plus 3 times -2 gives us -6. And that gives us -2 plus 4 -6. And that's the reason why you see CO3 2-. So therefore, the oxidation number of carbonate is 2. Why are we saying this? This is the charge of the ion. However, when you want to get the formula of the compound, you don't need to put the negative sign. You just need to point out that the number there is actually 2. So that's simply how you get the oxidation numbers of these elements. You can try more elements and you continue to get the concept of how simple this thing can actually be. We'll try a few more. Let us see. NO3 minus. Again, what happens in this case? Oxygen. I already put the charge anyways, but we'll be solving it later. Oxygen is -2. It tends to gain electrons. And then nitrogen, the configuration is 2,5. Oxygen is 2,6. Because oxygen wants to gain 2 electrons, it is -2. And nitrogen has to lose all of its electrons. So the oxidation number is 5. Since it's losing, that's +5. So when we have NO3, what do we have? We have +5 plus 3 atoms of oxygen times the -2. That means we have +5 -6. And that gives us -1. So we have NO3 minus. So the oxidation number is simply 1. So you can see that is how we get all these things. The concept again relies on the idea of electronegativity. Now, let us see this. NH4. We all know it as ammonium. Again, the concept, if you are asked which one loses and which one gains. Nitrogen, we already know it is 2,5. Hydrogen, we already know it is 1, simply 1 in the atomic shell. Nitrogen again, in this case now, is much more electronegative than hydrogen. And to form the octet, how many does it need? It needs only 3. So you can see, the one that wants to complete its shell, you ask how many it needs. The one that is losing, you ask how many it has to lose. So to complete octets, nitrogen needs just 3. That means it's going to be gaining 3. So in this case, nitrogen becomes -3. As for hydrogen, it is losing its 1, so it becomes +1. So when we calculate it, we have NH4, we have -3 plus 4 atoms of hydrogen. So you have -3 plus 4. -3 plus 4 gives us 1. And that is why you have NH4 plus. So the oxidation number of ammonium is just 1. Simple concepts. All about oxidation numbers. So from what is combining, you know what is supposed to gain and what is supposed to lose. So what is supposed to lose? How many does it need to complete its shell? It becomes negative. And one that is supposed to lose, how many is it going to lose? That becomes positive. You combine them together and you get your answer. Now, there are some which we call transition elements. That brings us to, let's see this one. This one looks nice. May look difficult, but actually it is quite simple. So the concept here is these are 26 and 25 and 286. They don't work after the first 20 elements. They start having issues. So what we focus on is on using orbital configurations. So I'll take a little space here to do that. Chromium is atomic number 24. When you write the orbital configuration, well, just to introduce us to orbital configurations, normally I could have written it as A arrow 4s2 and then 3d4. Something like this. But I'll be doing that. Because I'm trying to introduce the concept, I will write out the full thing. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. If you don't know this, fear not. Very soon, we'll be dealing with electronic configurations, and we'll be dealing with both types. So now, for transition elements, how do you get their valence electrons? Well, their valence electrons is simply what you have in the 4s orbital added to what you have in the 3d orbital. So that means that in the 4s orbital you have 2, and in the 3 orbitals you have 4. So that means that for chromium, its total valence electron is going to be 6. In this case, that is 2 plus 4. Remember, they exhibit variable oxidation states, and this is one of the reasons. All right, so, and you know, whenever you have a metal and a non-metal, except for hydrogen at times, the metal always donates to the non-metal. That simply means that chromium, with its 6 valence electrons, will be plus 6. And oxygen, as usual, we already know, is minus 2. It needs to gain 2 electrons. Oxygen is in the first 20 elements, so our 26, 28, and whatever is definitely going to work. So we can calculate it now. We have C arrow 2 O7. Chromium is plus 6, so we have 2 atoms of chromium, which is 2 times plus 6, plus 7 atoms of oxygen, which is 7 times minus 2. This gives us plus 12. 2 times 6 is 12. Then plus 7 times minus 2 gives us minus 14. Plus 12 minus 14 gives us minus 2. So therefore, you are going to find C arrow 2 O7. The oxidation number is 2 minus. So the oxidation number is simply 2. That is how you get these things. All right, and finally, let's take one for manganese. Again, manganese has atomic number 25. That's Mn25. Again, full configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, in this case 3d5. Again, once again, always check out at the channel. You will see when, and hopefully very soon, we'll be talking about electronic configuration. Now, what is the valence electron? Remember, it is the 4s electrons added to the 3d electrons. So 2 plus 5 means that it is equal to 7. And because it's a metal, it will most likely donate to the non-metal. That means plus 7, and oxygen, as usual, is minus 2. So our calculations for MnO4, we have plus 7 plus 4 atoms of oxygen times minus 2. So then you have plus 7 minus 8, which gives us minus 1. And that's how you have MnO4 minus. So the oxidation number is simply 1. So many of these radicals are the radicals you are going to be seeing in your exams. And that's why the focus is on them. So they are easy. Even if you don't know them, you can easily calculate them. Know their configuration, know what donates. If there are two nonmetals, the electronegative, which is more electronegative. And then if it's a metal and a non-metal, the metal obviously is going to donate and the non-metal is going to accept. That tells you which is positive and which is negative. However, like I said at the very beginning, chlorine, we said it has an oxidation number of 1. However, it can vary. But that plus 1 is simply its most common oxidation number. That's why I give an example in ClO4. In this case, chlorine here exhibits an oxidation number of plus 7. It's combined with oxygen. You can remember the concept. It is combined with oxygen. So what happens? Which is more electronegative? Oxygen is more electronegative. So oxygen will like to do what? It's much more likely to gain. Electronegativity is the tendency to accept electrons. So oxygen in this case needs 2 to complete its outermost shell. Remember, oxygen is 2,6. Then for chlorine, it is 2,7. But in this case, it is combined with oxygen, and because oxygen is much more electronegative, oxygen attracts the electrons. That means chlorine, as the guy, is the one who is going to lose. So he's going to lose everything in his outermost shell, which is now plus 7. So you're going to be having ClO4. So you have plus 7 plus 4 atoms of oxygen minus 2. So you have plus 7 minus 8, which equals minus 1. So ClO4 is actually minus 1. So the oxidation number is simply 1. And just like that, you have what you need when it comes to calculating oxidation numbers. You can see chlorine, it may not always be 1, it may be 7. It depends on the compound where it finds itself. So continue to work on this. Once you are familiar with this, then I promise you, the next video where we'll talk about formula of compounds is going to be as simple can be. And that is, as always, is our aim in Tutor-E Chemistry Hub. As usual, like, share, and don't forget to subscribe.